Welcome to our guide on handling regression with AR1 disturbances. This presentation will cover practical implementations in Stata, focusing on HAC, Prais-Winsten, ARMA, and Garch models. Our goal is to provide a clear guide for economists, graduate students, and researchers using Stata for time series analysis. As the quote on the slide says, time series data is a history of the past, but the error terms shouldn't repeat it, highlighting the core issue we aim to address today. This guide has been compiled by the Viet-Lod Econometrics Group. Economic data points are rarely independent. For instance, this year's GDP is highly dependent on last year's GDP. This creates a memory in the data, where high inflation today predicts high inflation tomorrow. This violates a key assumption of OLS, which requires errors to be uncorrelated. As illustrated in the graph, independent errors are randomly scattered, whereas autocorrelated errors show a clear pattern or trend. The core of the problem is that the covariance between an error term and its predecessor is not zero. When this assumption, cov of epsilon t minus 1, is not equal to 0, we have what is called serial correlation or autocorrelation. Ignoring this serial correlation leads to critical issues. First, you'll have biased standard errors, which gives you false confidence in your results. Second, this leads to inflated t-statistics, causing spurious significance where variables appear impactful when they are not. And most dangerously, it can result in spurious regression, making you find patterns or relationships that do not truly exist. Why this matters? If you ignore serial correlation, your seemingly significant results, often denoted by a p-value less than 0.05, might actually be false positives. The key concept to remember is that in time series data, the past predicts the future, even in the errors. This slide presents a decision flowchart to guide us from diagnosing issues in regression residuals to applying the appropriate corrective methods. The process begins with diagnosing residuals using Stata commands like estat bgodfrey for serial correlation or estat arch-lm for volatility issues. If you detect serial correlation, you then face a choice. If you trust your coefficient estimates but not your confidence intervals, use HAC or Newey-West to fix only the inference. However, if you believe the serial correlation invalidates the estimation process itself, you should use Prais-Winsten or Cochrane-Orcutt to correct the estimation. If the symptom is a dynamic mean, where past values of y predict future y, you would turn to ARMA or ARIMA models. Finally, if you observe volatile variance or volatility clustering, where periods of high volatility are followed by similar periods, the appropriate cure involves Garch or Garch models. The decision rule on the right reinforces this. Use HAC when your coefficients are reliable but confidence intervals are suspect, and use Prais-Winsten when the estimation itself requires correction. This slide provides a comparative overview of key time series methods. The HAC, Newey-West, is for robust inference, adjusting standard errors while keeping coefficients unchanged. Use the Newey command in Stata. Prais-Winsten is a GLS estimation method that assumes AR1 errors and transforms data to remove autocorrelation. Its Stata command is Prais. ARMA models are used for capturing dynamics in the mean of a series, where current values depend on past values, and the command is ARIMA. Lastly, Garch models are essential for modeling time-dependent volatility or risk, with the Stata command Garch. The key takeaway is that there isn't a single best method. Your choice depends on whether you are interested in modeling the trend, mean equation, or the risk, variance equation of your time series. First, the HAC, Newey-West, method adjusts the covariance matrix kernel of the estimators. It doesn't re-estimate the model, but rather corrects the standard errors to account for autocorrelation. This typically results in larger standard errors, SEHAC greater than SEOLS, reflecting the true uncertainty. Second, Prais-Winsten, GLS, is a method that fundamentally transforms the data before estimation to remove the correlation. The transformation is y star t equals yt minus rho yt minus 1. The parameter rho is crucial as it represents the correlation between errors. If rho is close to 1, it signifies high serial correlation, rendering standard OLS invalid. A key nuance is that the older Cochrane-Orcutt method drops the first observation, resulting in n-1 observations. However, Prais-Winsten saves the first observation, keeping all n observations. For this reason, Prais-Winsten is often preferred, especially when dealing with small samples. An ARMA model has two parts. The ARP, or autoregressive part, captures momentum, where past values of the series influence the current value. The MAQ, or moving average part, captures shock persistence, where past error terms influence the current value. ARMA models are the workhorse of macroeconomic forecasting for variables like GDP and unemployment. Garch, or Garch, generalized autoregressive conditional heteroscedasticity models are used when we observe volatility clustering, that is, when calm periods are followed by calm periods and chaotic periods are followed by chaos. These models have two equations, a mean equation, yt equals x beta plus epsilon t, which models the trend, and a variance equation, sigma squared t equals gamma naught plus alpha epsilon squared t minus 1, which models the risk or volatility. They are essential in finance for modeling stock returns and inflation risk. The absolute golden rule of time series analysis in Stata is to first declare your data as a time series using the tsset command. Without tsset timevar, none of the time series commands or operators will work. Once you've tsset your data, you can use powerful time series operators like L for lags, F for leads, and D for differences. For HAC standard errors, use the Newey command, specifying the maximum lag to consider. For Prais-Winsten, the command is Prais, and the corc option specifies the Cochrane-Orcutt transformation method. For ARMA and ARCH models, the commands are ARMA and ARCH respectively, where you specify the orders of the autoregressive and moving average components. If you want to regress GDP on its own lagged value, after typing tsset year, you can simply run regress GDP l.gdp. The L operator is a convenient shortcut enabled by tsset. This slide outlines the essential steps for data preparation and diagnostics in time series analysis. First, we prepare our data, which might involve transformations like taking the natural logarithm of a variable, as shown with generate ln GDP equals log of GDP. It is crucial to always visualize your raw series first using tsline varname to understand its behavior. Next, we declare our time variable using tsset year, which is fundamental for Stata to recognize the time series structure. After preparing the data, we run an initial OLS regression with regress yx. The critical step then is to diagnose the residuals. We can use tests like estat dwatson for the Durbin-Watson statistic, or, more robustly, estat bgodfrey for the Prais-Godfrey LM test. A p-value, prob greater than chi2, less than 0.05 from the Prais-Godfrey test, implies the presence of serial correlation, indicating that our OLS estimates may be inefficient or biased. As a best practice, always start with a visual inspection using tsline. If you observe upward trends in your data, it's advisable to consider differencing the variable, e.g. .var, to achieve stationarity before running advanced models like ARIMA or ARCH. This helps prevent spurious regression results. This slide demonstrates how to diagnose serial correlation in Stata. We start by loading the dataset, then declare it as a time series using tsset. Next, we run a standard OLS regression with regress USR idle. To diagnose for autocorrelation, we use the Prais-Godfrey LM test with estat bgodfrey. The output shows a p-value, or prob greater than chi-squared, of 0.0000. Since this p-value is less than our significance level of 0.05, we reject the null hypothesis of no serial correlation. This leads to the conclusion that our OLS model is invalid, and we need to apply a suitable cure to address the serial correlation. This slide demonstrates how to cure autocorrelation using the Prais-Winsten method in Stata. The corc option applies the Cochrane-Orcutt transformation. We can see that the estimated rho, the autocorrelation coefficient, is 0.57, which confirms a significant level of correlation in the errors. The most important result is the Durbin-Watson statistic, which significantly improves. The original Durbin-Watson statistic was 0.73, indicating severe positive autocorrelation. After applying the transformation, it moved to 1.72, which is much closer to the ideal value of 2.0, signifying that the problem of serial correlation has been effectively addressed. Here, we delve into Practice B, focusing on modeling volatility using Garch models. Our scenario involves analyzing the volatility of the wholesale price index, or WPI. We estimate an Garch model with both ARCH1 and Garch1 terms, using the command arch d.lnwpi, ARCH1, Garch1. The output presents a mean equation, where the constant has a significant p-value of 0.000. More critically, we look at the variance equation. The Garch L1 term, representing the reaction to past shocks, has a coefficient of 0.204. The Garch L1 term, which measures the persistence of volatility, has a significant coefficient of 0.695, with a p-value of 0.000. This Garch term is highly significant, and its coefficient is approximately 0.7. This strong persistence implies that volatility shocks die out very slowly. In practical terms, it means the market remains nervous for a long time after experiencing a shock. Ultimately, a model is only as good as its residuals. After fitting a model like Prais-Winsten or Garch, you must check the new residuals to ensure the original problem has been solved. The goal is to have residuals that are white noise. A white noise process has three key properties. First, the residuals should be random, with no discernible pattern. We can check this visually using an autocorrelation plot with the AC command in Stata. Second, they should be centered on 0. And third, they should be pattern-free, meaning the autocorrelation plot shows no significant spikes after lag 0. If the residuals look like white noise, your model is well specified. Imagine the residuals are like the static on an old TV. If you see a clear picture or pattern in the static, something is wrong with your signal, your model. If all you see is random, meaningless noise, you have a good, clear signal. Let's now summarize the key takeaways and best practices from our discussion. First, visualize your data with T-Sline to get an intuitive feel for trends and volatility. Second, formally test for serial correlation using estat bgodfrey after running a baseline OLS. Third, choose the appropriate method based on your goal. Newey to fix standard errors only, Prais to fix the estimation itself, or Garch to model variance. Finally, always verify your final model by checking that its residuals are clean and resemble white noise. A crucial expert tip is to never forget stationarity. Before applying any of these models, especially RMA or Garch, you should test for unit roots using a test like d-Fuller. If your data is non-stationary, you must difference it first to avoid spurious results. This brings us to the end of our presentation. Thank you for joining this presentation on regression with AR1 disturbances. To further your understanding and skills, we have a few next steps and resources for you. First, we encourage you to download the dataset that was used in this slide deck